Hmm. Okay, last video in Unit 13, and in this video we're not concerned about aromaticity, but I do put a bunch of reactions that deal with benzene rings. Now the thing is, if you recall, this whole unit was to convince you that benzene is pretty unreactive, that benzene, it being aromatic, is very inert to most reactions. So if we have this benzene ring, okay, and let's do um, maybe just BR2. You would think that whether you have one equivalent, two equivalents, or three equivalents, you'll start doing addition to the double bonds. But we have no reaction. In the next unit, we're going to look at reactions that actually do bromination on the ring. Um, what else? We could do... Oh, now I'm drawing a blank. Bromination, chlorination. Oh, we could add other groups like nitro group. We could add a methyl group. But for now, we're going to consider benzene pretty inert. We could do HCl. And you might imagine, well, for a double bond, you add an H and a chlorine. Here, no reaction as well. Okay. Hydrogenation. Under normal conditions where you have hydrogen and platinum, you can't hydrogenate benzene rings. You have to use a lot of pressure or high temperatures. But under ambient conditions where normally a single double bond will react, when you have something that's aromatic, inert, no reaction. We're going to see reactions on benzene in the next unit. And the main word here is on benzene. How do we get stuff onto the ring of benzene? For these reactions, we're going to do reactions that are off of benzene. And our first reaction is something we've seen, at least a reagent we've seen, but not used in this fashion. This is reaction 13A. And again, we're not going to put stuff onto the carbon of the benzene ring. We're going to do reactions that are off the benzene ring. And that is oxidation. Huh. What do you mean oxidation? We don't have an alcohol. So how are we going to oxidize a benzene ring? Well, like I said, we're not going to oxidize any carbon of the ring itself, but we will oxidize what's called the benzylic carbon. The benzylic carbon is the carbon that is hanging off the ring. You've heard of allylic carbon? Well, technically this could be think of as allylic as well, right? It's off of the double bond. But because we have a benzene ring, we'll give it a special name. This carbon is called a benzylic carbon. And that carbon is reactive. And the reagent we're going to use is Jones reagent. We're going to do a Jones oxidation. K2Cr2O7. So one combination of reagents to make the Jones oxidation work is potassium dichromate with sulfuric acid. Okay. Normally, if there was an alcohol, like if this was, well, not this, but if you had an alcohol that's oxidizable, like a secondary alcohol or a primary alcohol, yeah, you'll make the carboxylic acid or the ketone. But in this case, it's kind of a weird reaction. You got to find your benzylic carbon, and all you're going to do is oxidize it to the carboxylic acid. We're not going to look at the mechanism. We're not even going to even ask ourselves, well, where did the hydrogens go? What is this oxidant doing to do something like this? We don't need to worry about that. You should know that we make benzoic acid. No mechanism to be seen here. Okay, I'm not going to go through that mechanism. It's an oxidation, right? You're almost like burning the molecule, right? When you take a molecule and you add oxygen to it, you're combusting it, you're burning it. So that is one example of, how would we call it, benzylic oxidation. Okay. I'm wondering if I'm spelling that right. Yep. 1L. Now here's something a little bit unusual. Well, what if we had two methyl groups? Or what if we had two alkyl groups? Let's put a isopropyl group there. Let's have a methyl group right here where we know what's going to happen to that methyl group. And I do want to put a tert-butyl group. Let me draw you the result, and let's see if we can come up with um, how to verbalize what's happening so we can memorize the product, or at least figure out what the rules are in drawing the products. We could use chromic acid, H2CrO4, okay, instead of using the combination of potassium dichromate and sulfuric acid. But look at the product we get. And let's see if we could come up with some generalizations as to how to deal with other benzene rings that have alkyl groups on them. Already, you might notice something a little bit odd. Okay. Hopefully now you see something very odd. It seems like we oxidize this carbon here and this carbon here. I'm pointing at the benzylic carbons. And when I oxidize a benzylic carbon, you do make the carboxyl group, even if there's other carbons attached to that benzylic carbon. Those just come off as other carbon products like soot, smoke, carbon dioxide, char, because again, we're thinking about burning. Oxidation is burning. You're adding oxygen. What about this one? Whoops. It did not, got a paper cut. It did not get oxidized. It stayed as a tert-butyl group. The rule with this is that you need at least a hydrogen, one hydrogen on the benzylic carbon to get this reaction to work. So there's no hydrogen on benzylic carbon in this case. Don't oxidize. That's the rule. Why that is the case, again, we'll have plenty of mechanisms in the next unit, unit 14. Okay, so let's not worry about the mechanism for benzylic oxidation. I actually never mentioned that. While we have no reactions in this unit that are happening at a benzene carbon, we will see reactions on benzene in unit 14. Here we're using reactions that are off the benzene. Okay, that is benzylic oxidation. If you have to do a synthesis, right? If you have to do a synthesis where you make a benzoic acid, or we could call this a dibenzoic acid with some other alkyl group, see if you could get a methyl group onto the benzene ring, and then do an oxidation. Okay, right? If you start out with benzene and you want to get this benzoic acid, you need a carbon off of the benzene ring somehow. I haven't told you how to do that. That is unit 14. Another reaction, reaction 13b. We're going to see a reagent that we should be familiar with, just like here. We should be familiar with Jones oxidation. What about this one? Oops, let me get a drink. Let me pause this. I'll be right back. I'm back, but I don't know if I'm gonna, if you see my picture anywhere on the screen, so you won't see my face, it looks like from now on. Kind of a glitch with the program. I think when you pause it and you come back, you lose the picture in picture. uh, End of the semester, starting to lose my voice. Reaction 13B, we're gonna do benzylic halogenation. And really, it's just going to be benzylic bromination. We're not going to add a chlorine to the benzylic carbon. We're always going to add a bromine. Again, benzylic. So we need a carbon off of the benzene ring, and we'll just use this one. Oh, by the way, I didn't do any nomenclature for this unit. It would be nice that you know that when you have a benzene ring with a methyl group, this is called toluene. It's a popular solvent in the organic lab because it's very nonpolar, so it could dissolve a lot of nonpolar molecules. Um, all right, so for toluene, you've seen this reaction before. Maybe not the reaction, but you've seen this reagent before, NBS. You used NBS to do allylic bromination. Well, you're going to do the same thing. You're going to do benzylic bromination. And you have this. Let's use line drawing. You have that. Okay. Um, Is there anything going to be unusual if we use a more complicated alkylated benzene like this? Let's double check. Again, you are assuming, if you're in my class, excess reagent. So if you could brominate or put a halogen on the benzylic position multiple times, you will. And here we have NBS. Okay. Remember with NBS, it's a substitution. So you need a hydrogen to replace to make space for the bromine. You're not going to lose any carbons like we did for oxidation. So for this one, yes, we do have a hydrogen to replace. For this one here, we do have a hydrogen to replace. So those two bromines are at the benzylic position. But for your tert-butyl group, what? We don't have a hydrogen here. So how can you put a bromine here? You're not going to lose a carbon. Do you remember what the intermediate is? Let's take a look at our first reaction. It's a benzylic radical, right? This is a radical reaction. And just like for allylic radicals, you have resonance stabilization. You could have resonance stabilization for this also. You're not spreading the charge, but you are delocalizing the unpaired electron. Okay. I won't go through that, but you all should know how to draw the mechanism arrows to get the radical on this carbon, then to this carbon, then to this carbon. Um, so yeah, it halogenates there because you're making a very stable radical, right? The bromine goes at the most stable uh, position of the radical. Okay, that is benzylic halogenation with NBS. You don't need to know the mechanism for this. Next is something that we've definitely seen, and that is Wolff-Kishner and Clemmensen. I'm going to go ahead and give it a notation because we're going to use Clemmensen and Wolff-Kishner in a very specific way for this unit and for the next unit. So this is a reduction, right? Uh, and we'll just call it, let me do it this way. Remember what Clemmensen and Wolff-Kishner does? It removes the carbonyl group altogether, and you're left with a CH2 group. Let me show you in the context of a benzene-containing molecule, though. In the next unit, there's going to be reasons why we want to make something like this, okay? If you think about where our starting material is, or what possibly our starting material was, it was a benzene ring, okay? Most likely. And we're going to learn how to add groups to the benzene ring in unit 14, and one of the groups could be this. But ultimately, we might want to get rid of this carbonyl group. And to do that, you use Clemmensen or Wolff-Kishner reduction. Clemmensen zinc mercury amalgam, like an alloy, under acidic conditions. And yep, just like we did with aldehydes and ketones, we're going to do the same thing here. Okay. And you know that you could also do the same thing with Wolff-Kishner. Wolff-Kishner was under basic conditions. It was hydrazine and KOH. It will do the same reaction. The reason why people learn both ways is just in case there is a part of the molecule that is sensitive to acid. And if you don't want to touch that part of the molecule, maybe you should switch over to the base version of this reduction and keep that acidic group, or not the acidic group, but the group that is susceptible to acid safe by using the base version, and vice versa. If you have a group that is that reacts in base, but that you don't want to react in base, then you would use the acidic version. Okay. Right now, you don't know why we would want to do something like this. You'll see in the next unit. The next unit is going to be plenty of reactions and mechanisms, but also synthesis. And we're going to be using these, I call them side reactions. You could call them reactions on the benzylic carbon. We could use these reactions in synthesis to make really interesting molecules. Last one, reaction 13D. This one's a weird one because we don't have a benzylic carbon. What we do have is a nitrogen off of the benzene ring. Some textbooks take care of this reaction in the following chapter, but I'm going to take care of it right now because it is a reaction that we're not doing on the benzene ring, we're doing a reaction off the benzene ring. And that is another reduction of nitro groups. A nitro group is NO2. And what we're going to do here is we're going to make a anamine. Lost my words there. We're going to do this by first reacting with iron and HCl. And then the next reaction would be a little bit of base. And you'll see why in just a bit. We reduce that nitro group to anamine NH2. Okay. So there's a couple things here. At this point, I really haven't told you I don't think in any of the previous units what NO2 looks like. Okay. You might remember from general chemistry though that for nitro groups or the anion nitrate or nitrite, I think, no, just nitrate, that nitrogen is positively charged. Your Lewis structure actually looks like this for a nitro group. Okay, so can you see how it's we can consider it a reduction? We're getting rid of bonds to oxygen and we're replacing them with bonds to hydrogen. That is a good way to spot a reduction. Okay? Now the thing is, if we do the reduction just with iron and HCl, you'll have the NH3 plus, the protonated amine. And typically you want the neutral benzene with the amine group. This has a special name, and this has a special name. And just like we talked about toluene, right? That is the IUPAC name for this molecule. Okay, it's not called methylbenzene. Okay. These also have IUPAC names that you would want to memorize. This one is called aniline, a benzene ring with an NH2 group. This one is called nitrobenzene. Nitrobenzene. Okay. And that's it. This unit was mainly about aromaticity and how we could use that to predict the reactivity of molecules that either become aromatic when you, like in an acid-base reaction, or also we use aromaticity to figure out stability of charged molecules. We did have a couple of reactions at the end, but those would be most helpful after we've gone over the next unit, Unit 14, and we're going to incorporate these 4 reactions into syntheses. Okay. So that's what you have to look forward to. We're going to start doing reactions literally on the benzene ring in Unit 14, adding stuff to the benzene ring.